Thank you for coming so much to our second campus lecture of the semester. Today, we are so excited to have Bashi Mandava joining us. Bashi is a PhD candidate in physics, a fourth year in the Berkeley Center for Theoretical Physics Phenomenology group, working on dark matter, direct detection, and general beyond the standard model physics ideas. Today, she will talk about self-interacting dark matter and how it can lead halos to collapse and try to broach ideas that cosmologists and particle physicists alike are thinking of in this niche area. Please join me in welcoming Bashi.
Okay. Thank you for having me, guys, and thank you for joining. I made this talk last night and with mostly undergrads in mind, so this will be a very rough surface level talk for the grads here. But there's not a lot of particle theorists besides Ivan, so I'm hoping that it's still something fun and interesting and new that you're going to see today. But as Tucker introduced, I'll be talking about the gravithermal evolution of self-interacting dark matter halos today. Oops. Oh, I see. This is a PDF. So I cannot click the buttons. But the outline for this talk will be, I'll give you a one-slide introduction to this and immediately go into the case for dark matter. Hopefully you're all familiar with this idea of some extra mass in the universe and convinced that it exists, but I will make my case anyways, and then go into this relatively a bit more recent idea of self-interacting dark matter and the astrophysical effects of such halos. And then I'll show you guys some astrophysical data that we have and what those observations are telling us. And as particle physicists, what are the sorts of models we can write that would still be consistent with the data that we observe on cosmological scales. And then I might show you a slide or two of ongoing work that I'm doing personally, but that will be very brief as it will take a few more months for that work to progress. This is a very weird way to give a talk. Okay, so there we have it. That's the standard model. It's big and beautiful and really hard to read this Lagrangian, but it's also extremely simple. All of that jazz can be boiled down to basically 12 plus 5 parameters or particles, usually broken down into fermions and bosons, where fermions are making up the matter content of our model. So you have the up, down, strange, bottom, top, charm quarks, and then leptons, electrons, tau, and their neutrinos, and then we have the force carriers as well. All this to say that the standard model is very, very pretty and an extremely successful theory. We were able to predict the electromagnetic moment up to very, very big, significant figures. I think this is probably the most precise measurement we have in nature. But there are many outstanding issues that are not explained by the standard model: neutrino masses, hierarchy problems, dark matter, etc. Today, I will just focus on one of those, dark matter, by starting with the case for dark matter. So one of the earliest pieces of evidence that we have for the existence of dark matter came from galactic rotation curves. This is a plot from Rubin and her collaborators, I think stemming from like work in 1970s. I think the first piece of evidence actually came in 1930. But basically what you're seeing here is that using your usual Newtonian physics, you can predict what the velocities of stars moving about in some galaxy should look like. So that V equals square root gm over r. And so you should, if that were true, expect some 1 over square root r scaling for your velocities beyond some radius within which most of the mass in your cluster or galaxy is concentrated. What we actually observe from data is shown in this plot, where I would like you to focus on primarily the topmost line, where I think it's most clear that instead you see these velocities flatten out at some farther higher radii, which means, like, if you think of this in terms of Gauss's law, there is some extra mass that you haven't accounted for in your model that is leading to some mass scaling as the radius sort of parameterization that goes back into your velocity dependence and hence gives you these roughly constant profiles for your velocity dispersions. The second piece of evidence, which is a lot more subtle, but nevertheless stronger, comes from the CMB. So here you're looking at the angular power spectrum, which shows temperature fluctuations in the CMB across different angular scales. In simpler terms, basically, you look at the sky and you point a giant antenna at it, which is basically what the CMB is, and then you point in different directions and you measure the voltage in each direction. And if you do that, you get a 2D temperature map. And you can do some fancy things to this temperature map for you decompose it into mode spherical harmonics, which is what you're seeing here in this weird CL gadget. But all this to say that the angular power spectrum shows these temperature fluctuations and it has peaks in that spectrum. So different peaks that you're seeing here encode some important physics about the universe. So the first peak, to set this up, I want you to think of the early universe, the baryon photon plasma, as essentially a bunch of masses, baryons, connected by some springs or photons moving about in some gravitational potential well that is being sourced by dark matter. So as these baryons, or as this potential sources, as the dark matter sources this potential, all of your baryons and photons get pushed into these wells, and the baryons, due to their mass, are going to try to compress this fluid. Photons, due to their pressure, are going to sort of decompress this fluid. So you see this nice dance, or usually people refer to this as acoustic oscillations, sound waves. And the idea here is that every single peak that you're seeing here represents some sort of minimal or maximal density when the CMB picture was taken. So the first one is when these masses fall together and they haven't had time for the photons to decompress this fluid yet. So that primarily just depends on the total matter in your system. So that's sensitive to the total matter density of the universe. And the second peak that you see here is when the photons have had time to decompress the fluid. So you're looking at a snapshot where you've reached a minimal density now. But what's more important is that the ratio of these odd to even peaks, so you can think of this as a pendulum where your compressions are more sensitive to the masses in your systems and your rarefactions aren't. So the ratio of these peaks should give you a gauge for what is the matter in your system. And that gives us what the baryonic density should look like. And finally, we have the third peak, which is more relevant to the talk today, where if there were no dark matter, these potential wells that I was talking about should be much shallower. So the third time that you try to compress or fall back into these wells, you would do that a bit less efficiently than if dark matter weren't in your system. But you can't see that in this plot just yet. They look very similar. But if you were to zoom in on this third peak, you would notice that the third peak is ever so slightly higher than the second peak. And that the fact that the third peak is actually higher than the second peak or any prior peak means that you have dark matter in your universe. This is one of the most direct indicators of its existence, and also a lot more subtle than rotation curves. Yes, go ahead.
Type of that peak, because dark matter should be you will have more dark matter than the common materials, right? So is the height of the peak is proportional to the density, or does the height of the peak has any physical meanings?
Yes, the amplitudes do have a physical meaning, but it's not a one-to-one correlation where yeah, you would see it blow up. Yeah. Okay, so with that, hopefully I've convinced you that dark matter exists. And the next question we want to ask is, well, what is it? And the most straightforward answer I can give you is we don't know. We've been trying very hard to figure that out, but we only know certain characteristics about it. We know it's dark because there can be no significant interactions with photons, or we would have seen it in some detector. It has to be cold, meaning non-relativistic over cosmological scales. And usually we take the collisionless paradigm. And this bit I will come back to actually to motivate how we can think outside of the box there and introduce some sort of self-interacting model. And stable over cosmological timescales. If it were to decay, it would very strongly interfere with structure formation, meaning that we wouldn't see any like major galactic structures, humans, etc. as well. And then finally, the mass is where we have this big, beautiful plot ranging about 100 orders of magnitude. And theorists have built up some crazy cool models in every inch of that parameter space. So there's no shortage of models here. We can place bounds on the extreme ends, but as you can see, it's still 100 or roughly 100 orders of magnitude. So you can take it two ways. One, we're really bad at this. Two, it's exciting because you have all this theory space where you can build up models and go do some fun stuff and build up detectors based on those models and keep looking because it still is one of the biggest like outstanding issues that we have with the standard model. And while we have not found dark matter yet and have zero results from all of the direct detection searches that we currently have, it still leaves a bunch of parameter space for us to like collaborate with condensed matter physicists, astrophysicists, and other areas of research and probe different scales of cosmology and particle physics, etc. like that. Hopefully, seems like an exciting area to go into further. Yes.
Can I ask how the primordial black hole model would like permeate through dark matter? Is that just like a bunch of small black holes that are just everywhere in space? Or
Yeah, it has some pretty strong constraints, but the idea there is that they should have formed through some inflationary model. But yeah, we clearly haven't found them.
but like do the models predict like large black holes that are really spread out and they're just like all in one black hole? Or is it like
No, they predict like, yeah, so that mass scale is actually like you predict some tens of solar masses for the mass range. So you can't go higher than that. And then there's a lower bound there as well, depending on like Hawking radiation and stuff. But I don't know like the density of them. But you do predict like black holes of that mass in certain like astrophysical areas.
yeah, I guess my question was, is it heterogeneous across all or homogeneous across all space, or is it heterogeneous like it's all those specific spots that we're looking?
I think more specific. Yeah. Okay. Sorry, this is it's fun to slide to my next slide. Oh wow. Oh, it actually works. Okay, great. Okay, perfect. Okay, so the next question we want to ask is, well, how do we find it? And here, this question can be answered vastly differently depending on which dark matter model you're looking at, so which mass range you're focusing on. Here, I'm roughly looking at the light dark matter WIMP regimes, and the main strategies here are direct detection, indirect detection, and collider searches, where with direct detection, you look for interactions with target particles through some nuclear electron recalls. So your dark matter comes in and hits some crystal or some electron sitting in your detector, goes on its way, and then you look at, well, how did my detector react to that? So depending on your crystal versus fluid versus something else, those responses change. And this is where you can do a lot of like exciting condensed matter physics, because you need those experts to tell you how this material will react. And then you have indirect detection, where you can look for byproducts of dark matter annihilations and decays to other standard model particles, and collider searches, where you can try to produce dark matter particles in high energy colliders. And we've done a lot of exciting work on all of these fronts. I focus primarily on the direct detection angle. So I will try to connect the ideas that I'm presenting to you through the rest of the talk back to direct detection. Oops, okay, okay. Right, so those are the primary avenues that we've looked at, traditionally at least. Now, I want to think a little outside of the box, where now we say, well, so far I've talked about collisionless dark matter, but what if dark matter actually interacts with itself a bit more strongly than we thought? And by than we thought, I mean than the CDM only model. Okay, so I won't be going into much detail on what the dark sector is or what the physics there is like, but I want you to envision basically like a mirror world where you can have all the richness and the complexity of the standard model, except with some dark particles, dark atoms, some dark symmetries, etc. So here you have your standard model and you have the dark sector where in the most minimal case, you just have one dark matter particle. And the candidate here I'm using is like chi, and then some force carrier, phi, which I will refer to as the mediator. And they have some self-coupling. So with that model in mind, we want to think about, well, what are the physical implications of these? What should I expect in like observations and the data that I'm seeing? So here you can have direct detection searches again. So dark matter interacts with some fermions, with some standard model particles in general, or dark matter interacts with itself, and this can modify halos, which is what I'll focus on. Or dark matter can annihilate into the mediator particles, and that can then annihilate into some other standard model particles that we can observe. But for the rest of this talk, I'll just be focusing on this, on the middle one, and ask the question, if this model were correct, how would these self-interactions modify the astrophysics and the data that we see there? And in order to do that, we need to do two things. One, we need to understand how the evolution of these dark matter halos around us, like even the Milky Way halo has a huge dark matter halo. How would that evolution change, under these self-interactions? And to do that, I will present the gravithermal fluid formalism. And then the second thing you want to think about is, if this theory were correct, then how would, as particle physicists, describe the self-interactions? Like this is going to be an input in this gravithermal fluid formalism, which means we also need to be careful with the exact model we're using to describe the cross-section with which these particles are interacting. Okay, so this will be a very quick slide. But basically here you can model your halo as a fluid. We're going to ignore all sorts of like complicated physics. We're going to assume spherical symmetry. We're going to take like an isolated system. And for that, you can actually write down a very nice analytical system gone by these four equations. So here we're enforcing four things. The first is the mass conservation, basically just saying that mass should be conserved within some enclosed radius. Hydrostatic equilibrium, where you're balancing your pressure gradient with gravitational interactions of these particles. Heat flux, which describes how heat is flowing through this halo between different, even like mass shells between different radii. And you'll see this kappa gadget here, which defines your conductivity. Partly, the reason this system is complicated and we're doing so many assumptions, making so many assumptions to simplify this to some self-gravitating, isolated, no external effects system, is because this conductivity is quite hard to model. And we don't have a priori like a first principles calculation here. We have some approximations we can make in two extreme regimes, like the short mean free path regime, where your dark matter particles are interacting quite fast compared to the size of your halo, and then the long mean free path regime, where these particles can basically traverse the halo before ever hitting against another particle. So we make some more assumptions there. And then finally, we have this very long equation that is hard to explain and hard to understand, which basically enforces energy conservation, entropy, continuation. So you can think of the logarithm that you see here of v cube over rho as the entropy. And we're taking a time derivative there for each mass shell. So you keep your mass constant and you take this time derivative, and then you see how your gradient changes as you do that. And there are some prefactors to ensure dimensionality and the correct scaling with density and temperature, etc. But within the simplified system, you can then try to you can evolve these halos and solve for their density profiles, temperature profiles, velocity dispersions, and luminosities, etc., completely numerically. And most of this evolution proceeds in 3 stages. The first is the core formation stage, where initially you just start with a CDM cuspy profile. By cuspy, I mean like steep, or where rho is proportional to r to the alpha, where alpha goes like -1. I'll come back to this terminology a little to motivate like small scale problems. But to start off with, you start with a CDM cuspy profile, and then you have these dark matter particles interacting with each other, thermalizing your system, because they start like transferring heat from your outer hotter regions to your inner central regions. This is not yet a core. This is where the core starts to form. So depending on how strong your self-interactions are, that determines how efficient your heat transfer is. But regardless of those self-interactions, this is a very slow process in that it can take up to like gigayears, tens of gigayears for this to really, for the core to really form. Oops. And then once it fully kicks into this stage, you see this quasi-isothermal state with a flat density profile. So you lose all of this cuspy nature in your density at this point, up to some scale radius. This is not a very clear picture here, but you're isothermal more towards the core, and then your outer regions are still relatively cold. But now, because you have these outer regions that are still cold, your heat transfer is going to switch directions, and you're going to start, your energy is going to start flowing outwards. This bit is a little tricky, and the easiest way to understand that is to think about virialized systems. So for a gravitationally bound virialized system, you have E equals -T, which means that dE dt, your energy gradient with respect to temperature, is actually negative. This is a little counterintuitive, but this means that if you have a negative heat capacity in your system, even if you're losing energy, so these particle interactions can be like given towards the outer regions of your halo, kicking particles out sometimes, even if they're like violent. But as you start losing energy, your core actually increases in temperature, so heats up. And if your heat flux is not sufficient to prevent or stop that contraction, then your core is also shrinking at the same time. So your density starts blowing up, and you're shrinking and heating up in temperature. There's a weird terminology here because we usually interchange heat and energy, so raise in temperature and energy. But because you have the negative gradient here, these are not the same thing. Oops. Okay, to summarize, the evolution proceeds in primarily 3 stages. We have the core formation, where your self-interactions start to thermalize the core, leading to some flattened density profiles. And then you reach this quasi-isothermal equilibrium state. And if your self-interactions are actually strong enough, you can your heat transport is efficient enough that you can stay stable like this for a quite long time, leading to core profiles. And then finally, the final step would be the gravithermal collapse, where everything just starts shrinking and density starts blowing up, and you see this very weird steep central density. And this process is much, much faster. So the first 2 stages can take tens and tens of hundreds of gigayears to fully go through. And the final step actually proceeds in less than a gigayear. Okay, with that, I would like to now turn your attention to some problems with the CDM model and some astrophysical observations that we have. And then finally, I'll use the SIDM model that I just mentioned as like a possible solution to that, yes.
Setting or bounding the timescales of each of these.
Oops. So the first two, it should just go like 1 over. Oh, sorry. So the question was, what is setting the timescales for each of these regions? So I think for core formation in the isothermal core procedure, both of should just go like the usual 1 over rho sigma v. So I'm assuming some self-interaction cross-section there. So I think plugging in like 1 centimeter squared per gram, and then the usual Milky Way halo. So rho is like 0.3. And then for the gravithermal collapse stage, the density is going to look quite different. So it's going to be much higher. So you can think of the time scale becoming much shorter. But people also have more specific like time scales, like exactly where it kicks in, etc. But that requires a bit more complicated physics. Okay, so just to present like a very brief picture of the small scale problems in astrophysics, with the caveat that I'm not a cosmologist, so I might be saying things that are actually wrong. But hopefully there's no other cosmologists in the room. But basically these problems refer to discrepancies between the predictions from the lambda CDM model and observations of dark matter halos on subgalactic scales, meaning like below or kiloparsecs. So I'm presenting only 2 problems here. One is the core versus cusp problem, where CDM predicts cuspy density profiles, and observations find these cored flat profiles. And the second is the too big to fail problem, where CDM predicts Milky Way sized halos should host multiple massive subhalos that are basically too big to fail to form galaxies, meaning that whatever your predictions are, you should see some visible counterparts to those predictions, and we don't see them from observations. So to go into a bit more detail, in this plot on the left-hand side, you're looking at density, some dimensionless density versus some dimensionless radius, because apparently people like to present it as such. And I want you to just think about 2 lines here because there's way too much going on. The dotted line in the black, which is the NFW, or your usual collisionless paradigm model, and the dashed red line, which is an isothermal profile. So for the NFW, you would see this cuspy, very steep density profiles, and for an isothermal profile, you would see it flatten out, and observations tend to favor the flattened out profiles. And this is an issue across a wide range of systems. So people have seen this in field dwarf, in satellite dwarfs, in LSBs, in clusters, etc. And some of those, some of this problem can be explained by including like baryonic feedback effects, and that is what this group did. So here they're actually doing simulations by incorporating, well, if you have baryons in your system, which is a bit more realistic than the isolated halo model that I was talking about, how would that modify your densities? So they've shown that that can actually be a very good solution, but it is still limited to certain scales, meaning that so they're only considering dwarfs. And all this to say that there are other solutions beyond the SIDM model that I've presented that can explain some of these problems on certain scales. But there is no consensus in the field on this question yet. So we don't have a full solution. And like even I will tell you that SIDM can only solve this problem in this specific parameter space. So I'm not presenting SIDM as like this big solution to the small scale issues, but just that this is also something that we should be thinking about. So the second problem, like I mentioned, is the too big to fail problem, where on the left-hand side, you're looking at simulations that are just a solid line. And so that's going like this, and then your data that's also following a roughly similar profile, except it's an order of magnitude off. So your CDM prediction is telling you that you should have satellite galaxies that are about order 10, that are more massive than the observed most massive dwarf spheroidals. And on the right-hand side, it's a bit clearer. You're looking at the circular velocities of these galaxies, and the simulations are in pink. So you have this broad range where you have predictions for what this should work like. And then you cross-check it against data, which is in black. And you'll see that you only have data points for the lower half of this plot, which means that your simulations are predicting something in the upper half that we don't see. And that's an issue. That means that we don't see, there's no visible counterparts to the most massive subhalos from CDM. So what is stopping these galaxies from forming? Why don't we see them? So like I said, I would like to present SIDM as one possible solution to that puzzle. So through the gravithermal model that I just described, if your halos are in core formation, right, because you start thermalizing the core, your density falls almost immediately. And so instead of this collisionless, very steep profile, you flatten out your density because of these self-interactions. And the same for your circular velocities, because your velocity is parametrized by just the enclosed mass. If these self-interactions are violent enough that you're actually kicking some mass outside of your radius, then your enclosed mass decreases, and hence your circular velocities should also drop accordingly. Again, with the big caveat that this is only one of the solutions to these puzzles, and it's not a complete solution. But if you're satisfied enough with that, then you can start thinking about, well, what should I think of this model to look like on the particle physics front? What are the parameters that should go into this theory to accurately represent what we see observationally? So here I'm showing you a very nice plot that I haven't cited, that I don't remember which paper it's from, so I can't tell you. But it's a very nice plot of cross-section versus average velocities. So here you're looking at fits to observational data that show that these cross-sections favor certain values at certain scales. So if you're looking at these galactic structures, you can think of them as just deep potential wells that are sourcing these particles, that are pulling these particles in and sourcing their circular velocities. So the deeper the well, the higher you would expect the characteristic velocity to look like. So smaller objects should be on the lower end of this plot, bigger objects on the far right end of this plot. And usually in the field, people have like nominally considered just constant cross-section. So you take like sigma equals 5 centimeters squared per gram, and you stick that into every possible, you take that as a fixed constant instead of some parameter that you can vary in your model. But when we look at data, we actually see that all of this data, if you take, so you're looking at constant cross-section contours of 0.1, 1, 10, and 100. None of them quite fit the data. But if you take a dark matter model with the chi and the phi mediator that I mentioned, and with certain values for those masses, I think in GeV and MEV, you can draw a best fit through this data, and that's the yellow line that you're looking at. All this to say that your data is telling you that you need a velocity-dependent cross-section. Right, so observations from different systems are probing self-interactions at different velocities. Because bigger structures have deeper potential wells, this gives you higher characteristic velocities, which means lower self-interaction cross-sections. And as particle physicists, whatever theory you're writing, you should try to reproduce those effects so that we can, bring our theory a little bit closer to the data that we observe. So astrophysical data is pointing to a velocity-dependent particle physics cross-section. For that, in the field, usually people have thought of two extreme cases. The first one is just your hot sphere scattering, and the other is Rutherford scattering. So either sigma equals constant, or sigma goes like 1 over v to the 4. And these are both very good descriptions in certain limits. In more advanced language, that would mean in the heavy mediator and the massless mediator limit. But that is still only two cases that you've considered. Sigma can be some weird function of velocity. Sigma could be 1 over v cubed. Sigma could be 1 over v. Sigma could be et cetera, et cetera. But we need to include all of that parameter space. We need to include all of that physics if we want to do like a full analysis of these halos, at least from the particle physics front. So this is a bit more, from here on, the slides are extra material. But after you've included like the most generic velocity-dependent cross-section that you can think of, you can also go beyond the bond regime. Within the bond regime, this is straightforward to calculate. And then beyond the bond regime, you need to do some partial wave analysis and solve your Schrodinger equation with the Yukawa potential to obtain cross-sections. So it's not straightforward, but I don't have to do it. Somebody else has done it. So I just take their work and and go on with my life. So the stuff that I'm actually working on is combining two pieces. So the particle physics bit that I mentioned is we want to take velocity-dependent cross-sections, and we would like to ideally go beyond just first order. People have done that. And then the astrophysical bit is we want to evolve these halos for each resulting set of cross-sections. And this is where my collaborators come in. Professor Kimbody at U Texas wrote this very nice code, gravithermal SIDM, that basically does all of that. It's great. And then Mandava et al. Have written up more analytical approximations slash how do we understand this evolution. Turns out there is actually a universal evolution to these things. And my job now is to basically incorporate these two things together so that you can study the evolution of these SIDM halos of all sizes, not quite all, but almost there. And then one other idea I've been thinking about is instead of all of your dark matter self-interacting, because there's some strong constraints there, you can take only a subfraction of your dark matter as self-interacting, meaning that dark matter doesn't have to be one big like particle or theory that we're writing up. It can actually be like a bit more complicated than that. There can be several dark matter particles that interact differently, that have different underlying symmetries, etc. And here we're going to make an assumption that there's only a very small fraction of your dark matter that's has these self-interactions, meaning that on the larger scales, it would act collisionless again. But if that were the case, then you can also, open up some more parameter space on the particle physics front. And the evolution of the halo itself is not yet clear to me. We're still working on those details. So that should be fun in the next few months to work out. But this idea has been done before, slightly wrong back in 2014. So we're trying to redo that calculation. But we'll have to work it out to see if they were wrong or we are wrong. So we'll find out. But okay, to conclude, the standard CDM paradigm struggles to explain certain observed discrepancies at small scales. I presented two ideas, the Corcus problem and the too big to fail problem. And I'm presenting the dark matter self-interactions, which thermalize central regions of halos and lead to core density profiles as a possible explanation to these small-scale puzzles, while also maintaining CDM-like behavior at large scales so we don't interrupt or interfere with any existing physics that we already know is correct on the larger scales. And if you were to introduce an SIDM model, then the data tells you that you also need some sort of velocity dependence in your cross-section if you want to explain all of the data that we see on different scales like dwarfs, galaxies, and clusters. And I would like to think about the gravitable evolution of these halos under these interactions after incorporating some velocity dependence in your particle physics picture. And thank you. This is Sparkles. She's our community cat. Me, my roommate Will, and our neighbor Jim takes care of her. But she goes around to like 4 houses to eat. But it's somehow still very much not big. We were worried she was sick, but she isn't. She just has great metabolism or something. So she is, yeah. She's an outdoor cat until it's winter, and then she turns into an indoor cat. Okay, questions?
You quickly explain why Rutherford scattering to the 1/v4 depends, and then further what would be happening in the middle of that regime that's taken to the hard scattering regime?
Oh, sorry. I tried to go. Okay, yeah, let's go back to this. Oh, yes. So the question was, can you quickly explain like why Rutherford scattering was 1/v4 and what happens in this in-between parameter space? So the first one, I forget. I think it goes like, so you have some, so it should be proportional to your mass squared or dark matter mass squared, and it should be proportional to like, what is it? Another mass scale plus v squared sine squared theta over 2, and the whole thing is squared, so you get a 1/v4 in this limit. So we're assuming that m phi is much less than m chi v. So you can simplify that to just 1/v4. The in-between parameter space is the complicated stuff. So there is no analytical like understanding there. So this is why we're doing it numerically. So that in-between parameter space can be like broken down into the bond regime, the non-bond regime, the quantum regime, the classical regime, etc., etc. And it is complicated enough that these people wrote a paper on it. But in some regimes, like the bond regime, for sure, you have analytical expressions. But once you go beyond that, you just have to numerically solve it. But yeah, there's no one expression that we can think of here. And yeah, that space is not very intuitive to myself either. But all this to say, that is a complicated dependence that we want to include by using some numerical way of integrating these ideas.
You showed this for thermodynamics equations at the beginning. Is there any particular motivation for treating dark matter as maybe a thermodynamic liquid? Like where did that come from?
I think because it's easy. It shouldn't act like it, but it mostly acts like it. So it originally, like that idea originated I think in 19 something by Lidenbell and Eggleton. So they were applying those ideas to globular clusters originally. And that worked great. And then some other bloke came along and was like, well, what if we applied the same thing to SIDM halos? And it's actually a very good description, but it is not as accurate. So it can be accurate in some systems, like field dwarfs, for example, where your halo is more or less isolated because you don't have these like environmental effects of tidal stripping, ram pressure, etc. But then you have other systems where that can be a pretty big contributor to your physics. So in those cases, it would be a bad approximation. But all of that stuff is complicated enough that it's hard to incorporate like the realistic effects into the model. So we just stop there. Hey, yeah, you end.
Earlier, you gave some proof of, or I guess evidence of dark matter. I was just wondering how strong that actually is, how conclusive the graphs that you showed are proving that it's real or it exists.
I don't have numbers per se. I would say it's pretty conclusive. That's a bad way of answering that question, but yeah, I mean, there are still people in the field who work on like modified gravity and strongly advocate for it. But I think the overwhelming, like, yeah, there's a lot of evidence that goes beyond the 2 slides that I've shown for the existence of dark matter that I would say it's pretty conclusive at this point. But yeah.
Confusing how do you self-interaction dark matter model can solve the core custody problem because you also predict a core.
Sorry. Let's go back. Yes. Right. So it solves the problem in that, so you would naively from like CDM only models, right? You would expect this black curve. So there's no self-interactions there. But if you incorporate self-interactions into your model, you get this chord profile or flat profile. And that is what the data is showing you. So data matches the red curve, not the black curve. So you need to invoke these self-interactions to explain the data that we see.
Okay, the density profile is different with observations, not the core. Okay, thank you.
Yeah.
Questions? If not, thanks, Bashi, one more time. Thank you again for coming. Please feel free to sign in on your way out if you haven't already. We have another lecture next week with 2 postdocs. We'll be talking about electron microscopy. Hope to see you there and have a great evening. Thank you.
Thank you guys.